Hello, everyone. Hope you're doing well. I have marked out a title here because I forgot to change it before I compiled my PowerPoint. So it is properties of metric spaces today, especially those with regards to functions. Today we'll be talking about uniform continuity and convergence. So we're just now getting into the stuff that we're not going to be seeing on our upcoming exam, but we're going to be seeing these on our unit following here. Now, this is going to be one of the lessons that is going to be crucial for this. So even though we are kind of gearing up for other things this week, make sure that you are kind of keeping this stuff in your mind and aware of it, especially since there's a little bit different. There's a couple of very kind of sticky nuances here that are going to be important for us later on, but this is kind of a touchstone that we'll be coming back to as we move through the material of the next few weeks. In particular, we've seen some examples where continuity is not enough, where uniform continuity is a little bit better. And perhaps as well, we've seen an example of convergence not being enough, that we need something called uniform convergence to help make that make sense. So we've talked a little bit about these two topics. So let's say what these two topics are. We'll be defining those in this particular video. We're also going to go ahead and start introducing equicontinuity because we're going to start starting to analyze if we're looking at functional vector spaces, what do compact sets even look like? That'll be something that we start developing here in today's lesson. In particular, we've seen some examples already of things that do not work nicely here in terms of our functions like f of x equals 1 over x. This function, f of x equals 1 over x, is a continuous function, but it does not have a very nice extension to the entire half rule line going from 0 to infinity. We cannot take it to its completion. And the reason is that there's not really any place for it to go. The function is unbounded as you approach 0 from the right. And because of this, you're not going to be able to get a good extension of that continuous function. We've also talked about types of functions where, series of functions in particular, where we ask the question, is it true that if f sub n approaches f, is it the case that the integral of f sub n approaches the integral of f? And we've mentioned that a part of the answer to the problem here is that you could have a different type of convergence here than you're used to. Instead of it being a pointwise continuity convergence, you could be looking at a uniform convergence here. Now, these notions of uniform are very related, so I'll make sure to talk about these all today in the same video and talk about how these two things relate. However, one caveat of doing it this way is that it is easy to mess up. What does it mean to be uniformly continuous? And what does it mean for a sequence of functions to uniformly converge? It's easy to get those mixed up. Even though their ideas are so similar and we're presenting them together as a result, it's easy to now think of them as the same thing. So think a function can be uniformly continuous, but a sequence of functions can uniformly converge. Here is an example of something that is not uniformly continuous. And here we are asking the question, could these, if these sequence of functions uniformly converge, could their integrals converge as well? Now, notice that uniform convergence is not something that can apply to numbers. Numbers can only converge or diverge. That's all that they have to do. Uniform convergence applies specifically to a sequence of functions converging. So to be clear, uniform convergence applies only to sequences, and I'll underline sequences too, as we know that that's an important distinction, of functions. So only to this exact category is where I would say something converges uniformly, at least for the contexts of this class. So why don't we go ahead and jump on into it by starting with just looking at an individual function. Uniform continuity deals with a notion of just a single function. Now, we've gone through and talked about what it means for a function to be continuous, and we have that definition right here. I've written it in terms of quantifiers, and for this particular definition, it's easiest to think of this in terms of how it moves the quantifiers around. We would say that a function is continuous on a set x if for all points inside of that set x and for all epsilon that you could choose, that there exists a delta such that for all x values that are close enough in that little delta window, then their y values are close enough in that little epsilon window. That is our definition of continuity that we're used to. Uniform continuity is a little bit stronger. And what makes it stronger than continuity is it does not allow us to have this choice of x naught with the choice of epsilon. Whenever we choose this delta, for example, whenever we're trying to show that something like f of x is equal to x squared is continuous, then what we notice in that is that oftentimes that delta that we end up choosing relies on more than just the epsilon that we were given. Let's kind of walk through this argument to see it a little bit. Let's take f of x is equal to x squared and go through the same sort of scenarios that we would to show that this is a continuous function. Let's say it's at x equals 3. Well, what we need to end up with is the fact that x squared minus 3 squared is less than epsilon. So our typical way of solving this is we go through and factor x minus 3 times x plus 3, and having this be less than epsilon. Now, x minus 3 is the thing that we want to guarantee to be small. X minus 3 is less than epsilon over x plus 3. And we want this, basically our choice of delta now, to be able to be any x value that we might choose for this value of x. Well, we then make a choice for our delta to be less than 1. So that since x minus 3, since the absolute value of x minus 3 is less than 1, that will imply that the value of x can only be in between 2 and 4. Basically, we're saying that the distance between this point x and 3 is 1, and there's only the range of numbers between 2 and 4 that makes that work. Well, the smallest that I can make this value to guarantee this less than or equal to then is what happens when I plug in 4 here for x. So I end up saying let delta be equal to the minimum of 1 and epsilon over 7. Epsilon over 7 is what I get when I plug in x equals 4 for that branch there. Now, notice in that argument that I used heavily the fact that I was working with x equals 3 in terms of its continuity. Uniform continuity does not allow us to make that sort of decision. The function f of x equals x squared is continuous, but it's going to end up not being uniformly continuous because any argument that we can make for its continuity relies on this choice of x. If x was equal to 5, this value would have to be different. Because of that, we would then have to make an argument that says for all epsilon, there exists a delta. Our choice of delta has to happen here. Notice that we do not get to choose the x naught until after the delta is chosen. Think of this as like an assembly line where things are being given to us and chosen in a specific order. For continuity of f, we are given an x naught, and then we are given an epsilon. And then, in order to complete the game, I, the person who's completing this proof, must give a delta. The assembly line for uniform continuity is different. It says, for all epsilon greater than 0, now you give the delta. You do not get to use an x value. So notice that this argument would not work for uniform continuity because the delta that I chose relied on the value of x. So this uniform continuity is going to ask us to make a delta choice without knowing what the x naught is for our set. Everything else is exactly the same. We still ask for the distance between those 2 points to be less than delta, and for that to imply that the distance between the corresponding y values is less than epsilon. That's the difference between these two types of definitions. Continuity is typically done at a point because you get to use that x value, you get to use that epsilon, and then say, okay, I'm going to choose a delta neighborhood in the x values so that the y values are within that little epsilon neighborhood that was given to me. Uniform continuity asks for it to be even stronger. You do not get the x value that you're wanting to find. In fact, it needs to work for any x value on your set. An example of a uniformly continuous function, and we'll get to more of these later on, examples of these are things like f of x is equal to x. Because the way that I could go through and do the epsilon delta argument for uniform continuity doesn't really care at what x value I'm looking at. Whenever I do this, I say let epsilon be greater than 0, then choose delta to be equal to epsilon. Because then, if, let's say, absolute value of f of x minus f of x naught is less than delta, then the absolute value of f of x minus f of x naught Well, knowing what my function is useful, and I get that information with uniform continuity. I know f of x is equal to x, and similarly, f of x is equal to x naught. Well, I know that because this is absolute value of x minus x naught again, that this is less than delta, which is equal to epsilon. And that is all that I needed to show that f of x was continuous. And because I never needed to specify a particular x value, this is a uniformly continuous function. In the argument, I never needed to specify an x value when choosing my delta. That's the big deal. We'll see other characterizations of uniform continuity here as well, but this is the one that's most useful for proving things. Here is that definition all written out. Notice that the only thing that I've changed here is that instead of writing x and x naught, I've just written x and y as two given points. Think of this as like a symbolic removal of the base point x naught. In order for you to be continuous, you're continuous at a point x naught. Here, this doesn't really care about an x naught. It just says any x and y values inside of your set x. And if the distance between them is less than delta, the distance between their y values must be less than epsilon. Here is an example and a write through of why the function f of x equals 1 over x is continuous, but not uniformly continuous. I actually go through and use the negation of this definition, and you'll be asked to do this at some point in your homework as well. So you might try and use this as a little bit of a guide. Here, I pick epsilon equal to 1 and then show that for all choice of delta greater than 0, that there are x and y inside of this domain such that the distance between their y values is greater than or equal to 1. The choice that I end up using is I get two values of functions, 1 over n and 1 over n plus 1. In fact, I'm actually making sequences here to say that regardless of what delta greater than 0 that I might choose, this value, this difference between the two x values eventually goes towards 0. So it'll eventually be less than that delta value. So for example, if I chose my delta to be equal to 1 over a million, then I would say, okay, well, let n equal to a million. Because now I could say with these two functions that I could look at 1 over a million minus 1 over a million and 1. And that difference is going to be less than the delta that I've chosen. That's the reason for making these sequences, is that eventually, because these sequences get closer and closer to each other, that they will basically, the distance between them will get within any delta neighborhood that I want them to. Notice again, no base point. I don't need them to be centered at a specific point or even approaching anything inside of the domain. Both of these sequences approach 0. They just need to get closer and closer to each other. And then by definition, the difference between their y values is equal to 1. If it helps, try and unpack that a little bit about where these sequences are coming in as you start trying to go through these examples for uniformly continuous. The function f of x equals square root of x is uniformly continuous. So given an epsilon greater than 0, pick delta equal to the square root of epsilon. Then note that for any values x greater than or equal to y, and I've gone through and done a little bit of a notion here about why it is true that the square root of x is less than or equal to the square root of x minus y whenever x is the bigger number. And essentially what that ends up giving me is an inequality in terms of the differences between their y values. And that's essentially what goes on in this sort of scenario. Now, when I've gone through and done f of x equals square root of x arguments before, maybe I did rely on the fact that when I was trying to do continuity, not uniformly continuous, just the point continuity, then maybe I would use the fact, okay, well, I'm close to x equals 1/2 here, so I'm going to leverage that. Notice that this argument can be done that never leverages the fact that my x value is any point inside of that interval 0 to infinity. It could be any point. Any point in there would be okay, and this argument would still work just as well. Let's go through and show a class of functions as uniformly continuous. Let's look at the Lipschitz continuous functions again. Turns out that f of x equals square root of x is not Lipschitz, and I will be asking you to go through and check that yourself. This tells us that the Lipschitz continuous functions actually live inside of the uniformly continuous functions. That basically we have a kind of a concentric circles of all of these different types of functions. Lipschitz continuous works inside of here. Then we would have uniformly continuous functions up here. And in fact, you can show that all uniformly continuous functions are continuous. Think it's actually harder to show something is uniformly continuous than it is just straight up continuous. So this is kind of like the concentric circles we have of each of these different types of continuity. Let's show that the red circle is in the blue circle here, that the Lipschitz continuous functions are inside of the uniformly continuous functions. So we know that a function is Lipschitz continuous if the distance between y values is less than or equal to a constant times the distance between corresponding x values for some k value that is determined for the function f. Note, this constant cannot change as I change x and y values. This k is irrespective of whatever x and y values that I've given. So let's use that. So again, just to be clear of what we're looking for, we want to show that for all epsilon greater than 0, there exists a delta greater than 0, such that whenever the distance between x and y is less than delta, then the distance between f of x and f of y is going to be less than epsilon. So this is the goal of what we're trying to get towards. So when I'm building my chart, that's what I'm thinking of as my goal. If I'm starting to build from the end side, then maybe I use the fact that this distance between y values has a neat little bound in terms of the distance between x values. And I probably should be trying to find a connection between those two. Let's see if we can do it without making a particular choice of x. Well, I know that the distance between y values, by the definition of Lipschitz, that this is less than or equal to k times the distance between the x values. So k times the distance between x comma y. So what would I like my distance between x and y to be? Well, I will choose dx comma y to be, do you know? If this needs to be less than epsilon, what am I going to use as my choice of distance between x and y? Yes, you should choose that distance between x and y to be some sort of, or rather, my choice of delta is what I should write here. My choice of delta to be equal to epsilon over, we could write k, but we'd get less than or equal to for our formulas. And we know that less than or equal to is okay, but just to be clear, I'll write 2k in the denominator. The only reason for the 2 is so that I end up getting to write a less than sign rather than less than or equal to all the way through. So I'll choose delta to be equal to epsilon over 2k. Then if the distance between x comma y is less than delta, the distance between the y values, f of x and f of y, this is less than or equal to, by Lipschitz again. So now we're out of our scratch work and into this part, that this is k times the distance between x and y. This is less than or equal to, by our definition. Oh, I guess, yeah, we didn't need the 2, did we? Because we have a less than baked in here in our definition. But you'll just kind of see what I was thinking here. Less than epsilon over 2k, which is less than epsilon, which is what we desired. And that gives us a proof that, notice, never use the fact that I had a particular x or y value to work with. You might go back through your proofs that we did back in week 2 with regards to finding continuous functions and ask which of those functions was uniformly continuous and which one of those maybe is not uniformly continuous. Now, remember, you can't just say, oh, my argument used a particular x value, so that can't be a uniformly continuous function. That's not how that works. Remember, you can go back to some of the ones that perhaps you used x values for, like square root of x, and rewrite the formulas a little bit in a way that never uses the fact that you have x or y given when choosing your delta. In those particular cases, then you could kind of work through them in this sort of way. So something kind of neat to think about as you're going through and looking through these. The special nature of uniformly continuous functions is how they interact with compact sets. I mentioned that we would see compact sets over and over again here. And indeed, here we are. Let's take a proposition. Let f go from x to y be a continuous functions between metric spaces. If x is compact, then automatically f is uniformly continuous. So say, for example, you knew that your function was only defined going from 0 to 1. If you have that, great. Continuity is all that you need because continuous functions are automatically uniformly continuous. This is a great proposition that can save us a little bit of that time. It allows us to say, okay, yeah, we can choose X values if we need to for this argument, because we can just then invoke this proposition to say it's actually uniformly continuous. Our proof of this is assume starting that f is not uniformly continuous, and we'll go through and show that f is not continuous. Now, similar to what we did in our previous example, we're going to use the negation of uniformly continuous to say that there exist sequences x sub n and y sub n, such that the distances between the two of them get smaller and smaller, while the distances between their y value is greater than or equal to epsilon. Now, the reason for using this same sort of notion as what we did up in the slide 2 is that we now have sequences, and sequences converge in compact sets, even if they're just Cauchy. So take this d sub x, x and y in here, and take a subsequence of that x sub n that converges to a point A. Then take the corresponding subsequence here. Now, this is a little bit of a nuance. I've taken a subsequence of x sub n to get x sub nk. I'm taking that same corresponding subsequence of indices, but applying it to the other sequence here, the y sub n's. So this is y sub n sub k. So think if I had, for example, taken a subsequence of x sub n, which was 1, 2, 3, 4, 5, and I'm only taking the subsequence of 1, 3, and 5, then when I start looking at, and this is for my x sub n sub k, 1, 3, and 5, then when I start looking at what y sub n is, and maybe that sequence is 6, 7, 8, 9, 0, then I'm starting to look at y sub nk, which is 6, 8, and 0. Those are the indices of those parts of the sequence. So when I say I'm considering the subsequence y sub nk, I'm saying go ahead and only consider the entries in that sequence that correspond to indices that are left in the sequence x sub nk. Well, this corresponding subsequence y sub nk also has to converge to A as they grow closer and closer to x sub nk. So you can think there's a little triangle inequality argument there, that the distance from y sub nk to A is less than or equal to the distance from y sub nk to x sub nk plus the distance from x sub nk to A. And we know that both of these go to 0. This one goes to 0 because this is actually less than 1 over n sub k, and that's going off to 0. And then the distance from x sub nk to A is going to 0 because of convergence. However, at that point, it's impossible for both of these x, y values to converge to f of A as their point-for-point distance in y. They have to be greater than or equal to epsilon, farther away from each other. Well, then that means that one of these sequences does not converge to f of A. So we had just found the existence of a sequence in X that converges to a point, but the Y values don't converge to that point. And if you recall, that is the definition of normal continuity using the sequential formulation. So we've shown now the negation of continuity. A pretty neat argument, one that you maybe would not expect all that well, kind of working through it, unless you started working through the negations of these definitions first. Knowing what the negations of each of these are, and then seeing, oh, I have a sequence here. I could start utilizing this sequence because I know a compact definition that involves sequences. That's a huge jump to be able to make, and then start trying to build something off of that. As always, if you're going through these proofs, something I like to remind my students about is to be using those start and end charts that we were talking about back in week 2 to build something about, okay, what does it mean to start this? What does it mean to end this? And is there an easy way to connect those two things? Let's take a break real quick here and do something called equicontinuity. Now, this is not something we're going to use immediately, so I'm only bringing this up here as a blip. In fact, you won't see me do many homework exercises on this, but this does motivate something that we're going to be talking about later on in this unit, which is equicontinuity. A place where we may not expect to see compact sets, which we know are going to be coming up in this unit, is in the space of functions itself. We might ask the question, what sets of functions are compact in the space of something like, say, the continuous functions from 0 to 1? To visualize this example, we're going to first note that contractions f and r are differentiable and that the absolute value of their derivatives is less than or equal to 1 for all x and r. In fact, they have to be less than some value that is less than 1. So let's go through this example of the set of all contractions going from 0 to 1 to 0 to 1, where f of 0 is equal to 0. This ends up being a compact set in C of 0, comma 1. Let's talk a little bit as to why. So here's how this is going to work. I'm going to have a lot of text here, if in case you are kind of the more ready type of person, but I'm also going to be giving some pictures here. Let's start imagining what these sorts of contractions might look like. Well, contractions go from 0, 1 to 0, 1. So in particular, their slope can never go above 1. They're always going to go, like say something like this. They might connect 0, 0 to 1, 1. They might connect instead 0, 1 to 1, 0. That is allowed because of the absolute value for their derivatives. So they can go to -1 as well. And something else interesting is that their y values are stuck between 0 and 1. Their y values cannot go beyond that point. So let's start with showing about what is it about these that make these compact. Well, we're going to use the definition of compact that we just used in the previous proposition proof, which is that we want to show that any sequence, no matter how weird they are, of contractions, has a subsequence that converges to another contraction. In particular, all of these are going to be where f of 0 is equal to 0. So let's start by taking a look at this. How do we show that this is a compact set? Well, we're going to start with just a generic sequence of in C of 0, 1. Now, in fact, I actually wrote -1 to 1 here. So to be consistent with the rest of this, I'll go ahead and change this to -1, although it won't change much if we just leave this to be 0, 1, and sub out 0, 1 in all of our closed intervals. Just to add another example to make sure that we're kind of clear on what that might look like, I might start having a function that looks like this. So here's a function that maybe connects 0, 0 to 1/2, -1/2, and then connects us back to 1, 0. That could be another function now in one of our contractions. Well, if I take a look at all of the function values where I just isolate x is equal to 1 here, you might notice something about these x values. Well, they're all going to be in the codomain of this function, which is -1 to 1. So all of the y values are somewhere inside of this closed interval. Well, that closed interval is compact. In fact, the maximum distance between any two functions in f sub n is equal to 2. Why is this? Remember how we define distance between functions. The way we define distance between functions is we look to see what x values are the farthest apart from each other, and we say, okay, that farthest amount distance, that's the distance between those two functions. So for example, I could draw one more function maybe that goes like this, and that connects to 1, -1, and that would be two functions, the one here, this one, and the one here, this one. Those two functions would have distance 2 from each other in this perspective. But now, since that interval from -1 to 1 is compact, there's going to exist a subsequence of this sequence of functions, just looking at the x equals 1, that converges to a point in -1, comma 1. So given my subsequence of functions, so starting with maybe f1, f2, f3, f4, f5, and so on and so forth, I'm going to get a subsequence of functions so that their endpoints converge to the same point. So I'm going to have an f sub n1, f sub n2, f sub n3, f sub n4, and f sub n5, where this is a subsequence of this function, of this sequence that comes above it. So there's f1, f2, f3, f4, f5, our original sequence. We're now going to have them all converge to go to the same point here at the end. But I want us to notice something interesting that happens now between distances of functions that now all converge to the same point. Just for the sake of the picture, I'm going to assume that that point is 1, 0. Do you notice anything about the distance between those two functions of any two functions that not only agree at this point, but also agree at this point? Say they agree at 1, 0, just for the sake of argument. Well, think about the farthest distance that you could have between any of those two functions. You could have one that goes up here and goes down here. But again, because the slopes are in between -1 and 1, you can't have something that goes like that, right? That would not work. You can only have something that goes like this, or maybe something that goes like this on the bottom side. In fact, these are the extreme examples. Many other functions inside of here are just going to kind of look like this. And so the distance between two functions that are kind of like wave-like inside of here, that distance is going to be even smaller than the distance of these two red functions that I have up here. Well, what is the distance between these two functions? Here's 1/2, and down here is 1/2, -1/2. The distance between those two functions is 1. Notice that having these two functions agree at one point here at the very end is extremely useful, because now I can say that the distance between these two functions is 1, rather than the maximum distance being 2 from what I began with. So why don't we do this process again? Why don't we now say, okay, well, let's take the point 1/2. And let's say at the point 1/2, I would like to take these functions and say that there's a subsequence that where these functions all agree at 1/2 or eventually converge to it. So let's think a little bit about what is going to be happening there. Before I move on, I'll go ahead and mention real quick that I'm not necessarily assuming that all functions in this subsequence f sub nk have f sub nk of 1 equal to 0, or any point for that matter, but they are converging to it. So although their maximum distances between them may not be 1, it may be 1 plus, once I get far along enough, a very small number, some epsilon here. And so that is important to note as we kind of go through this. It's going to be 1 plus some sort of small enough number, but we could move along the function to make that number as small as we would like. And that's going to be important in what's kind of coming forward. Because we could do this again at 1/2. And remember, look at this. If I have functions not only that agree at 0, 0 and 1, 0, but also agree at 1/2, again, for the sake of argument, let's say they go to 0, then the way that those functions can be formed, the maximum distance between these is also severely limited. The maximum distance here is equal to 1/2, plus epsilon, of course, because of the fact of convergence. Some little epsilon is happening there. Same sort of stuff over here. We are going from maximum distance of 2 to maximum distance of 1 to maximum distance of 1/2. And so the goal for the rest of this proof is going to be to say, let's do that. Let's take a subsequence of our subsequence. We'll call it f sub n k1, f sub n k2, f sub n k3. That is, again, a subsequence of the original function that we said, okay, well, for all of these, their x equals 1 values converge to the same point. And then let's do it again so that all their x equals 1/2 points converge to the same point. And then let's keep doing this. Again, by shifting our function forward far enough, or by picking a number far enough inside of these subsequences, then I am able to say that that epsilon is something that I don't really need to worry about that much, because they'll eventually converge to that point. If need be, I could choose my subsequences to be far enough along so that, say, my epsilon here is less than 1/2. My epsilon here is less than 1/4, and so on and so forth. And I could just kind of keep doing this as I keep going along. So you can kind of see maybe what my pattern is here. My goal is to take this and continue to make subsequences of further subsequences. So what is the subsequence that I get? Because I can't take a limit of subsequences. That would give me no functions at all, because I'm eventually going to take out every single function. What we end up doing is something called a diagonalization argument, which we'll be kind of emphasizing a little bit next week as well. This diagonalization argument does this. It says, I'm going to take a subsequence like this, f sub 1, f sub n2, f sub n sub k sub 3. And then if I kept going to another subsequence here, this would be f sub n sub k sub l sub 4. And I'm going to consider this subsequence of functions. This is known as diagonalization. This might seem like a very much out there type of technique in terms of analysis, but this is actually used a good bit. Diagonalization is a neat practice that says I'm going to take a function, take subsequence that does what I want it to do. In this case, all of my x equals 1 gets values for this functions get close enough to each other. And then for the next function underneath, I'm going to make it so that all of the x values at 1/2 get close enough to each other. Maybe for my next one, I make x equals 1/4 get close to each other, and then x equals 3/4 as well. And I keep subdividing my intervals over and over and over again. And I just take the diagonal entries on that set. Well, I am going to get a subsequence. Each n value is bigger than the one that came before it because each subsequence is a subsequence of the one that came up above it. And what I end up getting from all of that is this sequence that has to eventually have distance between those two functions go all the way down to 0. Because again, think here, the maximum distance was, say, 2. The max distance here was 1 plus epsilon, where here epsilon could be chosen to be less than 1/2 if we go along far enough. Here, maximum distance was 1/2 plus epsilon, where epsilon could be chosen to be less than 1/4. And after enough times, we're going to get 1/4 plus epsilon, again, choosing sequence points that are close enough. We're guaranteed for this for convergence, all the way down to just 0. All the way down to 0. In which case, this is exactly the subsequence that we're looking for. This is a subsequence of functions, f sub n sub k, all the way down, and I end up calling this a different letter. I use g sub 1, g sub 2, g sub 3, so on and so forth. That gives me a Cauchy sequence. And since the set X, which really is the set C01, I should be writing here, is complete, then this converges to a function in C0, 1. Using the metric, it can be shown that this is indeed a contraction. Essentially, we're using things like the derivative. The derivatives work nicely here to show that this is indeed inside of the set. Contractions, f of 0 is going to be equal to 0. This is the least of our worries. We have something that is inside of the set that is a limit of a subsequence of the sequence that we started with. You might notice a little bit of similarity here with the proof that a closed totally bounded set is compact, but with this kind of addition of a diagonalization argument to be working with here. Hopefully the pictures are helpful and kind of help us understand what we're doing for the contraction, but the diagonalization component is going to be useful. At the end of the day, we don't want to be doing this with every single thing. With every single thing that we try and show is a compact set. We don't want to have to say, oh, let's do a diagonalization argument today too. And so what we're going to do is we're going to learn a theorem called Arzelà-Ascoli. And that theorem is going to say that if you have a set of functions that is equicontinuous, then with a couple of other conditions added onto it, you can go ahead and say that that set is bounded. And you'll see that the proof of that involves this diagonalization argument. So that's going to become important there. But I wanted to highlight what that is so that when you see that in the reading assignment for that week, you're not kind of taken aback. This is the type of argument that we are using here. This is diagonalization. So again, we do not want to do this every single time. So we're going to take a little bit to talk about equicontinuity. And I'll bring this up again in a future talk. I really just wanted to go through and give an understanding of what is motivating some of our push forward here. But when we get to our Arzelà-Ascoli theorem, I'll give this notion of equicontinuity once more. Briefly, this is going to be for a collection of functions. And it essentially says that for all epsilon, there exists a delta such that these functions are uniformly continuous, but utilizing the same delta, regardless of how many functions are given inside of our collection. So a collection of functions is equicontinuous if they're all uniformly continuous underneath the same choice of delta. So, for example, the set of functions f of x equals x, f of x equals 2x, f of x equals 3x, so on and so forth. If I consider the infinite collection of functions like this, where I maybe say f of 3 and this f of nx is equal to nx, this is an example of a set of functions that is not equicontinuous, because my choice for delta for each of these would have to change based on what value of n that I'm given here. Well, you might say, John, could I just choose delta equals epsilon over a million and take care of all of these other functions? That takes care of all the functions above it, but not the ones underneath it. And this has to be true for all given functions. So this is an example of a collection that is not equicontinuous. So it's asking that these functions are all uniformly continuous, but in the same way. Is one way to kind of think about it. These are all uniformly continuous functions, n times x, all uniformly continuous. But looking at how the delta has to change as your n value gets higher, these are not all like uniformly continuous, utilizing the same kind of bounds for x and y. Another way to think of it, I don't have that picture here, so I'll talk a little bit more about it in Arzelà-Ascoli, is to say that essentially all of these functions kind of do live inside of some little kind of window here that is small enough for a given function. Again, we'll talk a little bit more about this once we get to Arzelà-Ascoli, but I wanted to go ahead and bring that up, especially to go through this diagonalization argument. And then finally, pointwise and uniform convergence. Talking about sequences of functions like we just talked about there, we have considered sequences of real numbers to be working with, but we have not quite talked about sequences of functions, which are ordered lists of functions very much like the ones that I had just written down. F sub n is equal to nx is an example of a sequence of functions. If I plug in a value n, then what I get out is a function. Notice that with just this f sub n here, it kind of looks like I have a function of two variables, n and x. But you'll always see me use a letter like n, perhaps m or something like this, to signify that I do not want this to be a function of more than just one variable. Instead, I would like this to be something that when I plug in a value of n, that what I get out is a function of a single variable. So for example, f sub 5 is going to be 5 times x, and that's an element there in this sequence of functions. Another couple of other examples of sequences of functions, and we'll analyze this a bit more in our homework, is f sub n of x equals x to the n, f sub n of x equals x over n, and f sub n of x equals cosine of n times x. Now, I could have even just said f sub n of x is equal to x. That's a constant sequence with respect to thinking of this in terms of functions, because as I iterate my n value and make it larger, my function does not change. This would be a constant sequence of functions. Well, with these sequences of functions, how do we go through and define convergence? And we mentioned that there's probably a few different ways to do it. One of them we mentioned is converging pointwise to a function f. We would say f sub n converges pointwise to f if for any choice of x that we might get, and then for any epsilon, that there exists a n value cutoff, so that with respect to that particular x slice that we're making, the y values converge to the point f of x. So f sub n would converge pointwise to f if any x slice, taking a look at the y values as its own sequence, then that would converge. So for example, here we have the functions x to the n. These functions here could converge to 0 whenever, say, x is less than 1, or 1 when x is equal to 1. The picture of these functions, do I have it down here somewhere? Here it is. The picture of these functions looks a little bit like this. Here, this could be, say, y is equal to x squared, y equals x cubed, y equals x to the fourth, and so on and so forth. Continuing to build these functions gives us a bit of a steeper slope as we go toward the end. But remember, when you square a function that's less than 1, or square a number that's less than 1, it keeps getting smaller. Like 1/2 squared is 1/4, and then square that again, it gets to be 1/8. You can see how that kind of is how emblematic that is in taking a look at this sequence here at x equals 1/2. Well, that's going to converge to 0 at that particular slice. When I say x slice, I mean like the slice here at this particular x value. Looking at all of the y values, I see that that goes towards 0. At 1, on the other hand, that just sticks around and is 1, because whenever I take x equal to 1, x to the n is just 1 over n, which is just equal to 1. So that's why I end up getting this piecewise limit or pointwise limit of this function to be 0 when x is less than 1 and 1 if x is equal to 1. Over here, I also tell you what n value you would need to choose to go through and do this argument rigorously. In quantifiers, that's our definition for pointwise convergence, but there is an even stronger definition that utilizes the uniform part of it. Remember, for uniform continuity, we took the x values over here and moved them over so that when we got to choose our delta, at the time it was delta value, we did not get access to the x value that we were making our choices of convergence for. So if we write the x value over here, then what ends up happening is we are making a decision of what the cutoff point n is without knowing what the x value is beforehand. Now, that can be a pretty big deal, because notice for specifically these functions right here, that the convergence toward 0 really does depend on what your value of x is. If I had looked at these functions over here at x equals 1/2, that's a different story than looking like, say, way up here. Like, sure, yeah, those will go towards 0 eventually, but their rate of going towards 0 is a lot different as you get closer and closer to 1. Squaring 0.99 makes it a lot less small than squaring something like 1/2. So we'll say that that collection of functions would converge uniformly, namely that sequence of functions, I should say. If for all epsilon there exists an n such that whenever you have an x inside of your set and any n value greater than that cutoff point you've chosen, then the y values in absolute value go to be less than epsilon. So our choice of delta cannot rely on x. So going to this idea, is it true that the functions x to the n converge uniformly to f of x equals 0? Even on the interval from 0, 1, open on the one side? The answer is no. It still does not. We claim that there's always an x value such that f sub n of x has a value of 1/2. Note that that would always be an epsilon value of 1/2 away from the 0 function, where we're claiming that every point going from 0 to 1, not including 1, would converge toward. Indeed, you can actually solve for this. Take x to the n equals 1/2. Then you could actually go through and solve for n to get e to the negative 1 over n natural log of 2. That is an x value. So at that particular x value, regardless of what n value you choose, if I take that x value and raise it to the nth power, I get 1/2. So since this does not work past all cutoff points for n, we have f sub n cannot converge uniformly to f. There is no good cutoff point that works for any given epsilon. So this gives us the negation of uniform convergence. And that's going to be a big deal for us. We're going to want to know about what type of convergence are we looking at when we're looking at a given sequence of functions. Is it pointwise? Is it uniform? And we know that there are particular scenarios where stuff like that is very useful. Let's do one last exercise before we finish here to talk about this uniform convergence. Let's take f sub n of x equal to n times x to the 1 over n minus 1. So 1 over n again, there is the nth root, minus 1. And let's show that this converges pointwise to the function f of x equals ln of x. Now, I do have part of this as a homework exercise, but I also want to kind of notate a few things, getting my notes pulled up here. All right, I have found my notes. So let's show first that this converges pointwise, or at least explain why we should expect it to converge pointwise. Well, first, what is it about this function that makes us think that this could get us to the natural log of x? And here's a little bit of a hint. Let's think about another function or sequence of functions that kind of gets us closer to where we want to be. Here's a hint for this. The natural log of x is the inverse function of what function? It's the inverse function of e to the x. Natural log and e to the x are inverses of each other. And aren't there different ways to write the function or write the function e to the x? I have in our homework exercise exactly what e to the x is equal to as a limit as n goes toward infinity. This is 1 plus x over n to the n. Now, you might actually be familiar with this formula. How? Because if you take out the x here and just write e, then this is e to the 1, for example, is the limit as n goes to infinity of 1 plus 1 over n to the n. And you may have actually seen this formula for e before. This is indeed how we would go through and define Euler's number, e. So if I went through and plugged in x for this, then this is the type of formula that I would end up getting. There's a little bit of an argument to get from this step to this step, but what it ends up becoming essentially is I do a little bit of a change of variables to make this n equal to something like n over x. And then that ends up being kind of how I get to this formula. But you're okay to use that without proof. So this e to the x is the inverse function of the natural log of x. So let's say what happens when I take y equals n times x to the 1 over n minus 1 and make it like I'm taking an inverse for this function or trying to solve for the inverse. Remember, inverse functions is the flip over y equals x. So I'm going to be solving for the value y when x is equal to n times the quantity y to the 1 over n minus 1. And I'm going to go through and solve for y. So that's going to give us what? Something like x over n equals y to the 1 over n minus 1. And that's going to imply y to the 1 over n is 1 plus x over n, and this might look familiar. This is equal to y 1 plus x over n to the n. And there you go. So taking a limit with respect to n in this should give us something that looks like a limit with respect to this. Essentially, we're saying that limits work neatly over taking inverses, which is something that hopefully we could expect pointwise, that is, at any given point. So try trying to make some sense of this to try and show that this indeed is a good pointwise convergence. Now, should we expect this to be uniform convergence is a very good question. Let's think about this function for a little bit. This function, say on the interval going from 0 to 1. So let's analyze on the interval from 0 to 1. Should we expect this to converge uniformly to the natural log of x? Well, when I look at the natural log of x, I look at a function and I'm looking, especially when I'm looking going from 0 to 1, I look at something that looks like this. But what do these functions look like? N times x to the 1 over n minus 1. Since my x values are in between 0 and 1, my value of x to the 1 over n here is getting pretty is going pretty small, but it's actually kind of close to 1, isn't it? If I say, for example, took x equals 1/2 and then started taking bigger and bigger roots for it, I'm asking what number, if I take it to its nth power, gives me 1/2. Well, that's going to have to be a number pretty close to 1. So this number right here is going to be a negative number, but pretty small. And this value n right here is going to be good, or is going to keep maybe trying to push it down a little bit farther to try and counteract that a little bit. But at the end of the day, you might want to try and do this. Try showing that the function f sub n of x is bounded, whereas natural log of x is unbounded. So we want this to be true for all n, where natural log of x is unbounded. In fact, you should be able to go through and show that f sub n of x is actually in absolute value less than or equal to n. And so how are you going to get a uniform convergence for this? Think you need to be able to choose a delta so that you're always within an epsilon window of the natural log function when you can never get even close to anything that's down here, that's down at the lower part of this function. Because if it's lower than, say, for example, negative n, if it's lower than that, you're not going to be able to get within epsilon of anything but just maybe a couple of few variables. And you know that your function natural log of x is unbounded. It goes all the way toward negative infinity as x goes to 0 from the right. So that might be something that you kind of go through and try and piece together here as to why this may not be uniform convergence. Now, we've talked about a lot of different topics here, and today's session in particular, it might be good to be looking through this in some sort of depth. Make sure you're trying to take time for looking through all of these different topics and trying to piece them apart a little bit. Equicontinuity, we're not going to be talking about a ton right now, so you can kind of put that on the back burner as you go through and study. But try this difference between uniform continuity and uniform convergence. How do these things work? How are they similar and how are they different? And what applications would they have? But that'll do it for me today. Thank you so much. Have a wonderful day.